Hello everyone, I'm Kunal. I'm a PhD student at Louisiana State University working with Mark Wildy, and I'm currently working as a GRA at Los Alamos National Lab with Patrick Coles. This work was done in collaboration with Sumit, who is a PhD student at LSU, Marco, who is a postdoc at Los Alamos National Lab, and Patrick, who is a staff scientist at Los Alamos National Lab. And this was part of a summer school last year at Los Alamos National Lab. So these are our main results. We show that variational quantum compiling exhibit noise resilience to these noise models. And these noise models are very physically relevant because current quantum computers are noisy. And we extend our results to even general noise models by doing some simulations on IBM's quantum simulator. Specifically, we focus on QFT, Toffoli, and W state preparation circuits. So for past 2 decades, we have been aiming for these three applications: quantum simulation, factoring, optimization. However, our current quantum computers are noisy and they are NISQ devices, and we are limited by number of qubits, connectivity, gate alphabets, and also depth because there is too much noise. So what can be done with noisy devices? Well, we can do error mitigation, or we can do some variational algorithm. And the third application, which is part of my talk, is to come up with algorithms which have inherent noise resilience, maybe to certain noise models. So what is compiling? Compiling is to convert some high-level algorithm into some low-level machine code. And what do we mean by variational quantum compiling? Suppose you want to implement some unitary U on a quantum computer, and this could be some big matrix, let's say acting on 100 qubits. And maybe you figure out from classical algorithms how you can implement it on a quantum computer for a given connectivity and also for a given alphabet. But maybe the optimization is not global, and because the dimension of the matrix is very big. In that case, quantum computers can help us. So first we have to define what do we mean by compiling. Do we want full unitary compiling where we want to match the action of U and V on any input state? And another task is fixed input compiling where we just want them to be equal for a given input state. So what are the applications of VQC? Well, if you are really focusing on specific device, then maybe you can do device specific compilation better if you use VQC. You can also compress depth. And recently it has been shown that variational quantum compiling can be used for fast forwarding applications. And how do we do this quantum classical hybrid algorithms? Well, we can use classical computers for tasks for which they are better than quantum computers. For example, optimization. We can use gradient descent or other optimization methods for a given parameter set. And we can use quantum computers for calculating quantum things. For example, finding expectation value of some observable, which is difficult to do on a classical computer if the dimension of your system is really large. So once we define any task, we have to talk about these 4 questions, which is what is the cost function, what is the task for quantum computer, what is the task for classical computer, and how to perform optimization. So let me give you a sketch of variational quantum compiling. So suppose you want to compile some unitary U and you come up with some ansatz, which is V. And for device specific ansatz, we just consider whatever gates are available on a particular device, let's say IBM or Google or some trapped ion quantum computer. Now, quantum computer is used to calculate the cost function, and obviously cost function depends on your ansatz parameters. And once you calculate the cost, you feed that cost on a classical computer. And now let's say you let it go through some gradient descent or other optimization algorithm, and that gives us new parameters. So here I'm denoting parameters with K and alpha. Once you get those parameters, you again calculate the cost, and then this loop continues until the cost function goes down. So now the next question is, what is the cost function for variational quantum compiling? If we want full unitary matrix compiling, then the cost function is defined as follows. So let's say we start with all 0 state on system A and as well as B. And our goal is to implement unitary U, which is the target unitary on system A only. So in the initial part of the circuit, we are preparing maximally entangled state on n qubits. Then we apply U on half of those qubits. followed by our answers, and then we do the measurement in bell basis. So this whole circuit is just calculating this Hilbert-Schmidt distance between u and v dagger. And this is our cost function, and this is a global cost function because we are doing the measurement on all qubits. And it might happen that this cost function has barren plateau, which means that you cannot train v to find the let's say global optima. So that's why we also define a local Hilbert-Schmidt test, where instead of measuring all of them, we just measure 2 of them at a time. And why are these cost functions relevant? Well, because these cost functions have operational meaning. For example, the global cost function is related with average fidelity. So which means if the global cost functions goes to 0, then the average fidelity goes to 1. Average fidelity is the fidelity between output of u acting on any input state and output of v acting on any input state, and then taking the fidelity between those output states. And now the next question is the local cost function also faithful? The answer is yes. We have this relation where we can see that if global cost function is 0, if local cost function is 0, then global cost function will also go to 0. And it's efficient to compute on a quantum computer as well. So we consider these noise models: Pauli noise, non-neutral Pauli noise, and measurement noise. And these noise models are quite general because they have depolarizing noise and also amplitude damping noise. And measurement noise is we can just consider bit flip noise. So this is the noise model we consider in our circuit. So we have Pauli gate noise acting during the entangling gates when we prepare bell state, and we have Pauli noise just after that. We have global depolarizing noise acting during the implementation of U and V dagger, and we have non-neutral Pauli noise at that same time on qubits B. And at the end of the day, we also have Pauli gate noise when we are doing this bell basis measurement, and we have measurement noise. So let me define what we mean by optimal parameter resilience. So let's say you have a quantum circuit QC, and for a given algorithm, let's say for compilation algorithm, we define some cost function, which is a function of unitaries, the target unitary and also our ansatz. And we have, let's say, a noisy quantum computer, and the noisy channel N is acting. In that case, the cost function is given by this. Now suppose if we had done the optimization on a noiseless quantum computer, then let's say this is a solution. This is the optimal solution of quantum compiling. And let's say V tilde denotes the optimal solution when we have done the optimization on a noisy quantum computer. We say that this cost function exhibits strong optimal parameter resilience to this noise model if these two optimal solutions match. What we have shown analytically that for this particular noise model, we have strong OPR, which means if we do the training on a noiseless quantum computer and on a noisy quantum computer, we get the same solutions. We extend our results by doing numerical simulations, and whenever we do numerical simulation, we have to define our ansatz. So we define our ansatz by using this stress C0, which is a C0 preceded and followed by arbitrary single qubit gates. And we define two different kind of ansatz. One is fixed layer ansatz, where we have 2 qubit gates or 2 qubit C0, rest C0 acting on each of these qubits. And the second ansatz is where we randomly choose the location of rest C0. And this VK alpha is an arbitrary single qubit gate. We study this for 3 gates, Toffoli and QFT and also double state preparation. And these are so these are our answers just before showing our main results. And these are our main results. Here the dashed lines, the blue and this red dashed line corresponds to, let's say, if you have done noiseless training, and this denotes the minimum value of our cost function. Blue corresponds to the global cost function, pink corresponds to the local cost function. And this blue and green curves corresponds to the following. So let's say if you do noisy variational quantum compiling using your global cost function, And you can see that the noisy curve is sort of not going down. But now let's take the parameters through this optimization method and use those parameters to calculate the noiseless cost function, noiseless global cost function. And we can see that this green curve is going down even though the blue curve is not going down. And this green curve actually matches with the minimum possible value when you are doing the noiseless training, which actually shows that the variational quantum compiling, even if you have done it in the presence of noise, reaches to the correct solution. Similar thing happens with the local cost function as well. So this denotes the noisy training. If you use those parameters in a noiseless cost function, we again reach to the least possible value. So these first two curves, the top one is for Toffoli gate and this one is for QFT circuit. And these two curves are for our first ansatz, where we have the fixed layer ansatz. And the second and the last one is for the target inspired ansatz, where we can see that the cost function actually goes to 0. And with that, I'll leave on this slide. Thank you.